Okay, good morning, everyone. So we'll continue with where I left off a couple of days ago. And what I plan to do today, as I had in the program announcement, is kind of go over some of the applications of Bayesian methods to hydroclimate problems. And as you know, I come from an engineering department, so I come at this mainly from a pragmatic point of view. As to we have lots of problems, which methods makes the most sense, which ones give the most, which ones are easy and intuitive and best, and that's sort of how. And I have evolved over several methods in the last 10-15 years, so there's nothing religious about these methods. Okay, again to acknowledge all the co-authors and collaborators whose work I'll be presenting today and also tomorrow. So this is the outline that I plan, and I'll stop and time ends, and then I can fold it over in the last lecture. So I'm going to give a sort of a tutorial 101 to GLM, and then show connections to how it is just one step before the full-blown Bayesian. Then I'll show some hydroclimate applications that we have been working over the years. Also, I'll try to contrast specifically the three applications that I'll show, some what I call near Bayesian or almost Bayesian methods that are sort of traditional, some non-traditional. And the applications are the things that I talked about last time. I'll flesh them out a bit more. So the first application will be stochastic rainfall generator. I'll talk about what is it, what's the motivation, why we do that, and then how we bring the Bayesian hierarchical modeling and latent Gaussian processes, and then likewise forecasting. And I'll talk a little bit about extremes. That's something that I've been working quite a bit recently, and something to consider maybe as a next conference topic. So, okay, so let's start with linear regression. These are slides from my course. So again, I'm sure everybody is familiar with it, so we can go through. So you have y, which is a dependent variable or response variable. Then you have a bunch of predictors or covariates. And you want to fit a model that's typically of this form. So it's linear. Y is a function of x with some error. And it has the coefficient or parameter vector betas. And betas are obtained. So this is how your data is set up. So you have the augmented matrix, the response variable, the set of betas, and then the errors. You minimize least squares, and you get your betas. So pretty standard stuff, x transpose x inverse x transpose y. So viewed like this, you don't really need to invoke anything in terms of distribution and so forth until you get to inference, until you get to, if you want to put confidence intervals on y hat and so forth, then I got to invoke the data as normal or so on and so forth. But otherwise, until this point, it's pretty straightforward, and I'm sure many of you have used this, and people continue to use this in many applications. Then what you can do with the moving on is the estimator beta hat, which is the estimate of beta. You can show that it is unbiased. And then you can also come up with the variance of this beta hat, which simply turns out to be here. So it's simply x transpose x inverse with sigma square, which is the error variance. And you replace sigma square with sigma square hat, and that completes the process of getting the coefficients, the variation or the variance of the coefficients, and going a step further. I don't think I have that here. Okay, so you can also get sigma square, which is the error variance. So anyway, what I want to point out here is that until this point, it is pretty standard affair. So there's nothing. But where linear regression falls apart, or where it's not useful, is when your dependent variable is not normal. And that happens in many, many cases. And what people do typically is they try to transform, so do a log transform, power transform, try to make it as normal as possible, and then apply linear regression to that. And again, there are issues with that because then you are modeling the transformed variable and not the original variable. Several situations have data that are just simply not possible to transform, such as if you're trying to model rainfall occurrence, whether it rained or not. It's a binary process, 0, 1, and I'll talk about that in a little bit. Then you want to model number of wet and dry days, which are discrete numbers. And then rainfall itself, which is bounded and heavily skewed. If it's daily rainfall or daily flow in the river. So in other words, all applications that typically we encounter, I'm sure many others, tend not to fall in this normal category, but however, people just go ahead and apply and use it because it's pretty straightforward to implement it. So it is situations here where linear regression sort of gives way, and that's where we need something different. Okay? And that leads us to this GLM, or generalized linear model, which is sort of a much more general approach. So here, so some notations here. So X is your, like before, explanatory or covariates or predictors. Y is a set of observations, and then this is simply the likelihood. Okay. And what is done in GLM is, rather than fitting a linear model to the dependent variable, you fit a linear model to a suitably transformed variable of y. Okay? And the linear model is fitted to the parameters of the assumed distribution. And that sort of is where it departs and starts making it more general, the regression framework that we have used. So the idea here is your data is normally distributed. That's what you start out with. And in a GLM, it turns out all you need to make assumption is that y is distributed from this exponential family. And it turns out from this exponential family, you can actually derive all the distributions: normal, exponential, gamma, binomial, Poisson, and so forth. Okay? So you assume y is normally distributed. So as you can see, this is slightly different from the straight linear regression that typically people are exposed to. You just have x and y and fit your betas. And you specify sort of the 3 steps, if you will. So you fit a linear model in eta rather than fitting it to y. So that's one difference. And G inverse eta is takes you from the eta space to the mu, or the mean of the variable space. Okay? And then expected value of y given x is mu. Eta is the link function, or G of, so this here, eta, is the link function that transforms suitably the y, or aspects of y, and then you fit a linear model to that rather than fitting a linear model directly to y. Okay, and that's the key difference between GLM and the straight linear regression. Turns out that if you don't do anything, or if you don't provide any prior information on betas, and if you assume y to be normally distributed, this whole thing sort of collapses to linear regression. And I'll show that in a second. Okay. So you started out with this. So y is normally distributed. There's no reason why it should only be normal. So you can start with, if your data is binary, this can be binomial. I'll show that in one of my applications. If your data is discrete, it could be Poisson, and so on and so forth. Okay? So just as an example, this is sort of how you typically specify. So y is whatever distribution with the parameter, and the parameter mu I is linearly related, or some function of the parameter is linearly related to the covariates or predictors. Okay? And then you get your betas, and then you come back. In this case, the function, or the link function, is log, and then there are various, I'm not going to go into the details, there are various ways you can get link functions. Typically, these are what are known as canonical link functions that link up the mean of the distribution that you're considering to the predictors. And of course, this is the likelihood function, it's straightforward. Right? Likewise, if you want to model a categorical data, 0, 1, then yi is binomial with the appropriate parameters, and I being the, so in a typical case, you will have I going from 1 through n, the n observations are n data points. Okay. So for binomial, the link function is what is known as logit link function, and hence the term logistic regression. So if you have categorical data, you typically do logistic regression, and that essentially all comes from GLM. So you start with GLM, and if you assume binomial, then your link function becomes logit, and then this is your log likelihood. This is your likelihood function. So what I want to sort of summarize here is that linear regression falls apart in many cases, most of the application cases, and GLM provides a more generic framework. As long as your distribution is from this exponential family, then it turns out pretty much you can get suite of distributions that are typically used in practice to cover all types of data, categorical, discrete, continuous, and so forth. Okay, so what is this, or how is this sort of close to Bayesian? Okay, and I always do this when I got exposed to this. You could see that the way you prescribe this modeling framework is one of hierarchy. So you are saying y is some distribution with parameter blah, and this parameter or some function of this parameter is equal to blah, and you can actually add some more. So you can, there's no reason why to stop here. You can say beta is distributed as something else, and so on. Then as you realize that what was a simple straight linear regression, y is a function of x, suddenly is sort of, you're unpacking the whole thing. You have hierarchy that you can specify. And you can also specify other things. You know, there's nothing to restrict your hierarchy. You can add other things, such as if you have observational error that can get in, if you have information about your betas that can get in, and later I'll show that. But my point is that once you recognize that a simple linear regression can be written like this, you realize that you can provide a lot more in this hierarchy. And that's where it starts getting closer and closer to the Bayesian framework. Okay. So again, what I'm going to show here in this couple of slides is that if you assume normal distribution, and then if you do the if you take it to the Bayesian formulation and do the calculation, you actually get the least squares solution. So that's so you assume yi is normally distributed, and then your mu, which is the mean, is linear function of your predictors. So mu is x times beta. Beta is a vector of model parameters, and just like in a linear regression, you have two variables you have two sets of parameters. Your theta is essentially the coefficients beta, and then the error variance sigma square. So you have to estimate those two. Okay, and then you have some prior on this. Okay, so your parameter set is beta and sigma square. Okay, and if you simply keep it as it is and say I have no information on betas or sigma square, and I assume normal distribution, so the mean is linearly related to predictors, then going through the posterior, you actually get to this same solution as we had from least squares. Okay? So you have, so this is your prior, P of theta given y, so the Bayes theorem, and do some calculations. It's very simple algebra actually. It's a little bit of bookkeeping, but from here, assuming non-informative priors on betas and sigma squares, which essentially turns out that this condition is nothing but P of y, the likelihood function essentially, and it'll get you directly to this step, which is beta hat is x transpose x inverse x transpose y. That is the so beta, the posterior distribution of beta is normal with mean beta hat and this variance, and this, if you recall from few slides before, is exactly what we got from least squares. Okay. So what you get from minimizing least squares, which is sort of what we typically are used to in terms of doing regression, is now obtained via modeling it as a hierarchical, Bayesian hierarchical model. So that is sort of a nice thing. So what this does is it now provides you with a lot of possibilities, because you can add things about betas that you might know, you can add system error, process errors, and a whole bunch of things. Okay. So again, this is what is assumed here. So there's no information on betas and sigma square, and so which means just one, even though they don't look like PDFs or probabilities, but the fact that the posteriors give you valid probabilities, that's fine. And if you go through the calculation, you'll get there. Okay, and likewise for sigma squared, this turns out to be inverse chi-square, and this is exactly the unbiased estimator of the error variance in linear regression. Okay, so this is the mean value of this, and likewise this is the mean value of this posterior distribution of beta. Okay, so I think I have a summary slide, and then once you have that, then you can do the prediction. So if you want to predict y hat, then it's simply x times beta hat. You can take the mean value of the posterior distribution of beta and likewise the variance, and that will give you the prediction, and then using a t-distribution you get the confidence interval. So all of those that follows from in linear regression, the ANOVA, the t-confidence interval, everything sort of carries over if you want to get to get those quantities. So in summary, so what does GLM do? So GLM is hierarchical, right? And you can with specific distribution, it has a link function, and with simple step, providing priors and computing likelihoods, it actually takes you to Bayesian land. So again, if you assume normal distribution with no information on your parameters, then this collapses to straight linear regression. So the linear regression is a nice subset of the hierarchical modeling, and that's quite attractive. So that's why in that sense, the BHM is sort of a generalized framework of the generalized modeling. Okay. The other thing this is attractive here is that it enables you to now add in uncertainty in your model parameters, and also uncertainty in your model structure fairly automatically. Okay, and that's something I'll try and pull out during the examples. Okay, so here's an example of full write-up of Bayesian hierarchical modeling in the context of a logistic regression, and that will be my first application. So you can you can have your data as binomial distributed with these parameters, and the link function of the parameter is linearly related to the predictors. Beta can be non-informative, or you can add, so you can have priors on alpha and beta. So alpha is normally distributed with some mean and variance, and then the variance is gamma distributed. This mu and tau can be constant, or you can have in the full Bayesian, you can go all the way down. You can go mu is normally distributed with some other parameter and variance, and so on and so forth. So you can see you can expand to as much information that you have or that you want. Okay. Once you have this, then writing this is pretty straightforward. Then it's just Bayes' theorem and doing algebra and bookkeeping with binomial distribution, and that ends up with this posterior distribution here. So again, this is messy looking, so therefore you need a sampling algorithm, and there are quite a few of them. MCMC is sort of the more popular, the Markov and Monte Carlo, but you have Gibbs sampler, Metropolis algorithm, and so forth. So again, that's something beyond my scope here. Okay, so first application is stochastic weather generators, and particularly I'm going to talk about the rainfall occurrence and onset. So why do we need stochastic weather generators? Users meaning users of climate information, are most interested in their particular forecast of their particular sectors or processes. Okay, so for example, if you issue a forecast that the next 2 months average rainfall is going to be 20 centimeter, it's good, but it's of totally of limited use. If a farmer is going to use that information, he can't do anything with it. He needs more specific information of when does the monsoon season start, or when is the rainfall going to start, what's going to be the rainfall in the first half or first week. So in other words, they want a lot more information, or they want to know what's going to be the yield coming out of this season. So all those sectoral or process models, they require daily weather information for the next 1 month, 2 months, 3 months, and this includes a variety of crop yield, risk, disease models, all of them want what's going to be the weather scenario for the next season, month or so. But all what you get is typically one information, which is average precipitation or average rainfall and temperature. So you really need a model or a tool that can generate rich variety of scenarios of daily weather. Okay? To doing that, you have limited historic data, and that's not of much help. So it's not like you have lots of historic data to draw upon, so you have limited historic data, and you require to produce these daily scenarios of weather, so you need a model that can help you do that. Okay? And once you have that, it's driven through process models, and process meaning any of these. All of these have different models: crop model, watershed model, risk, and so forth. And out comes distribution of the decision variable, and then you can use this to make decisions. So starting at the start of the season, you can come up with what is going to be the distribution of the yield, or what is going to be the occurrence of a certain disease like malaria and meningitis, which might be useful then to feed into what kind of resources I need to stock up on vaccination or whatever. So whatever decisions that need to be made will require this quantity, but what you get from climate forecast is something that's crude and very crude in both space and time. Okay, so that's where the weather generators play a very crucial part. And this has been around for a lot of, almost I would say 20 plus years, but with newer methods coming recently, it's gotten a revised look from statisticians, and that's sort of what I'm going to project. And again, this is an example, some work that I've been doing in the Argentina Pampas region, so this is one of the agriculture-rich region, and again, to make decisions of crop planting, cropping strategies, you need stochastic weather generator to bridge that gap. Okay, so the application today is going to be in northeast Brazil, Brazil. So these are the individual locations where there is daily rainfall. So think of it as each one is a station or a location, and you have daily data, so there's about 500 of them here. And you have about 30, 40 years of daily data. And we want to model the occurrence. So if it rained or no rain, so it's 0, 1, and the threshold is 0.254 centimeters, so the rainfall on a day is greater than that. So the daily rainfall data that's available at each location is converted into this binary data, 0, 1. Okay. So at any given location, if you want to model what is going to be the, if you want to model the 0, 1 process, then as we saw from the GLM, the logistic regression is sort of the obvious model or the appropriate model. Okay. So Y, it's binary, binomial, and what we want to do here is to see if we can come up with a way by which we can combine information across space. So that's going to be the key thing here. Okay. So just to keep the notation straight, T, S is the space, so locations. Day, end of the year, and T is the time. And the parameter, in this case the logit function, has to vary with seasonality, right? So we know that the probability of rainfall at certain times is more than certain other times in the year, right? So to get that, you need these Fourier terms, or sines and cosines. And these omegas are simply annual cycles, so they span 365. So the parameter in this case, the logit link function of the parameter P of the binomial distribution is a function of sines and cosines. Okay? So if you look at here, you have a probability of rainfall on every single day at every single location for each year. So if you have 30 years of data, you have 30 times 365 values of probability that you are modeling. Okay, so this is the logit expression. Okay, the reason you have logit is that it enables that when you back transform, that the y variable is always between 0 and 1. Okay, so that's how you get the appropriate link function. Okay, so one thing you can do is you have 500 locations, and you can just go simply fit that previous model here, go fit it at every single location. Okay, so you have 504 models for all the locations in the region. So this is at one particular location, and you look at the coefficients. So these are the Fourier coefficients A, B, and C, and then this is the probability of rain for a given year, or average over all the years. And you can see that the probability goes high during the rainy season, and then other times it's less. So in other words, you're able to capture the feature. But what you see is also that you get some of these weird things which you are not sure. And the only reason, the way to get around this is you can borrow strength from space. So because clearly if you have 500 locations, there's a lot of information that's available nearby that you want to bring in. So fitting a model at each location does not bring that information that is available in space to sort of take care of some of these weird things that might be happening, maybe due to data or whatever, at any of these individual locations. And that's where going to a full Bayesian model sort of helps out. Okay? So what it does is it shrinks parameters towards a common mean, because clearly during the rainy season, even though you have 500 locations, a lot of them are going to behave similarly. Right? So there's going to be, if it rains, it's going to rain at a lot of those places. So there is a lot of redundant information, and at the same time there is information in space that you want to bring and try and compact your model. So that's what you want to shrink and get the parameters to sort of a global mean that can capture that spatial information. And you also get the parameter uncertainties are fully accounted for. So this is the Bayesian hierarchical model for this situation. So again, same as before, YST is logit, but it's binomial, rainfall occurrence at location S, time t, year n. But then these coefficients A, B, and C now are obtained from some prior distribution with some prior covariance function. Okay. Furthermore, these A, B, and C, the prior means of this normal distribution for these coefficients are themselves normally distributed with relation to latitude, longitude, elevation. So you can throw in all other information from your physics that you think are going to explain the occurrence of rainfall in that region. That would be lat, long, elevation, or if you are here, it would be distance from the coast, so on and so forth. So you can add all of that here. Okay, and then you also can have a prior. So this is the prior on the covariance of the AS, BS, and CS. So what is the advantage of doing this? Now suddenly, information that is in space, you can borrow strength from that, rather than doing just one model at a time individually. So now you take this and you compute the likelihood function. Of course, it's going to be quite messy because suddenly you have location, time, and then days. So years and days, and then you have all these parameters, multivariate. So you end up with this messy looking likelihood function of posterior P of theta given y, and of course you can use MCMC and let the computer run. So this was implemented in R, took about a week or so you can just let it go, and what you then end up with is the representation at every single location. Okay, and okay, so these are some results here. So this is at station 1, 2, 3. So 1 I think is in the north, central, and lower. And what is plotted here is that P, the parameter P, are the probability of rain on each day. So this is for 1968, 72, 1980, and notice that, and then these are confidence intervals coming from the Bayesian posterior. And notice that there is significant change from year to year. And that makes sense because some years are wet, some years are dry, and those are appropriately reflected in the estimation that in this particular year, which happened to be dry, that even during the peak of the rainy season, your probability of rain is 0.5, whereas here, it's more 0.6 or 0.7. Okay. So you can then use these probabilities and do a Monte Carlo and simulate. So you can then now simulate lots of scenarios of daily weather sequences or daily precipitation sequences. One other point I want to mention is in here, not only you can include latitude and longitude, you can also include elevation, you can include the seasonal weather climate forecast that is appropriate in that year. So you can add variables or covariates that are that make sense and that are of importance to the problem. And I think that is where this is a very flexible framework in that regard. Okay, and this is the average over. So this is for each of sample years. So you can average over all the years in historical record, and this is what you get at each of these different stations. And you can notice that clearly the station 1 has its peak around day 100 or so, whereas 2 and 3 have a completely different seasonality. And you can use this information to try and pull out which stations or regions tend to behave similarly, which is what we did here. So you can take the max probability of rain and cluster them, and you can see that all of these northeast has a different rainfall structure, then everything along the coast has a different structure, and everything inland has a different structure. So in other words, you have 3 different structures in terms of when the maximum rainfall occurs. So this is the plot of the maximum rainfall itself, and this is the plot of the Julian day when that maximum occurs here. Okay, so where you can use this information is now you can say the day when the probability of rain exceeds 0.5 is when the monsoon starts. So that gives you an objective measure to come up with the onset of rainy season. And furthermore, you can also come up with the uncertainty in that onset, and you can also use this for prediction for year to year. So those are all things that you can characterize. You can incorporate ENSO information, which I pointed out last time, and you can predict the onset and so forth. So that is all of that. Rest of it is described in that paper. But what I wanted to show here is that when we go from GLM to Bayesian hierarchical, and then a problem like this, which is quite daunting if you were to do it in a traditional multivariate, is much more tractable and provides all these uncertainties in parameters, uncertainties in the process quite naturally, and that's sort of the power of the Bayesian. Related application is sort of the one step before Bayesian. This is something that we worked on recently. It's 2012. Kleiber et al. Will Kleiber was a postdoc at NCAR that I worked with, and then now he's in our university in the applied math. So the latent Gaussian process, I must admit, I got exposed to this about 2 years or so ago from Will Kleiber. And again, they're very elegant, and they enable you to model space, and that's what I wanted to point out here. And again, as you will see, in terms of the model structure, it is hierarchical, so it is just a step away from full Bayesian. The minute you put priors and such, then you are in the Bayesian land. So this is what is done. Here we do both occurrence and amount. So in the example I showed before, it was just rainfall occurrence, so which means nothing to do with the actual magnitude of rain. So here we look at both the occurrence and also the amounts. So what we do is at each location we fit a GLM to get both of them. So that's what is done here. So you can think of it as it's just a straight generalized linear model. Probability of rain on day t depends on t minus 1, the sine, cosine, the seasonality, and then you can get a similar GLM for rainfall amount. That's alpha and gamma. Those are the shape and scale parameters. Okay, so this is something that you can fit at every single location. So you have daily rainfall data, and you can fit this model for occurrence, and you can fit this model for the rainfall amount. And you can notice that the amount depends on the occurrence. Okay, so what does the latent Gaussian process do? So what the latent Gaussian process does, it's somewhat like hidden Markov. So it says that this is the process that I'm observing. So it's 0 and 1. So if it rained, 1. If it didn't rain, 0. And there is a hidden process behind it, a Gaussian process, which if its value is less than 0, then what you observe is dry and otherwise wet. Okay. So this WS sub t, WST is a latent Gaussian process. S is space, T is time, and time going continuously in this case, 1 to 365, and then how many other years that you have. Okay. So this process has a mean, it's a mean function mu, and it also has some covariance. And the covariance structure I'll talk about in just a second, but it's basically depends on the spatial lag. Okay. So typically all these covariance functions are far away points have less correlation, near points have more correlation. Okay, so you have like an exponential decay type thing. The mean function is dependent on the predictors or covariance. So that's your x. So these could be latitude, longitude, sine, cosine, climate, whatever you want to throw at it. Okay, and so that's the covariance. And then you get this betas, set of betas. So the betas, beta 1, 2, 3, as many predictors as you have. So it's like a regression. And the only difference is betas comes with subscript s, so that means you have a vector of betas for each location in space. This is a covariance function. And then what you do is you have a model to model this betas across space. So right now all you have done is you fitted a GLM at every single location, so you have set of betas at each location. Now what we want here is we want to be able to generate weather at a point that is not observed, or some point in between. Okay? So right now there is no, the only way you can do right now is you simply interpolate the rain. So you take rain at say Chennai and Pondicherry and then interpolate it in between. But what this does is much more clever and quite powerful. It says you fit a model for Chennai and fit a model for Pondicherry, and you have a spatial model to interpolate the parameters of those models, so that if you want the process at some point in between, you get this beta sub s, where s is a point in between that need not be observed. So once you have your betas, then you basically have everything. So then you can generate scenarios. So that is the powerfulness of this approach, is rather than interpolating the actual field, you interpolate the parameters, and that is very clever, and this is something that comes over and over again in many applications. Okay. This Z is a spatial Gaussian process. So you started out here, so this is a Gaussian process for the occurrence. So this W is then linked to Z, and the only thing I would point out is this: the function type is what is known as a Latent covariance function. So Latent functions are essentially smooth functions. There are various forms of this covariance function. There's exponential, there's spherical, and Latent is sort of the more it's got good properties, and it's got 3 parameters, and it's like any typical spherical type function. So it's got those 3 parameters that you have to estimate: sigma square, shape, scale, smoothness. Okay, so the parameters are estimated in 2 steps. As you can see, there's quite a number of parameters. So what is done is you get the betas first through GLM. That is straightforward. It's nothing magical there. And then you estimate the rest conditioned on that. So you do it in 2 steps, and it turns out that the 2-step tends to be much more powerful and easy, converges better. And then lastly, we put together a likelihood function or MLE type function here, which is what is maximized to get these parameters. Okay? So again, just to summarize, at each location you fit the straight GLM model. That's straightforward and easy to do. And then you construct a spatial process model that for the parameters. And then if you want to describe the process at any location where you don't have data or where you have not observed, then you simply use the spatial process to get the model parameters. Okay, so we applied this to 2 locations. One is Iowa, which is flat as a pan, and then this is Argentina in the Pampas region. Okay, so as you can see, in Iowa you have about 20-25 stations. Same thing here, and just to point out here in the Pampas region, the farmers would like to make decisions, and also the regional government want to make planning decisions at the start of the season. They have crop models that they run over this region, and these crop models typically run on a grid, so which means at every single grid here you need daily weather. Obviously there's no daily weather, it's only there at these dots where you have observations. So how do you get the daily weather in between? So instead of interpolation, you can use this spatial model to get you to parsimoniously help you fill. So these are some results, and I'm just going to show just a couple of them. You can look up. So what you then do is once you've fitted the model, then you just simulate whole bunch, 100 years, 200 years, and then look at the statistics and compare those with the statistics of the historical data. So you want to see how good the model is able to capture. And so these are, for example, the occurrence probability between stations. This is the consecutive dry days, and so dry spell length. The solid line is the historical, and then the confidence intervals come from the model. This is at one station in Iowa, another one in Pampas, and these are all done in cross-validation mode. So you drop the point and predict. So remember, you also have a spatial covariance, which is changing from day to day. So here is the covariance structure for January 1st, the solid line and the dots, and here's the covariance for July 1st, and you can see that when January is the rainy season, and you have a much higher covariance or spatial covariance, whereas in July it's their summer. So in other words, it's quite different, and that is automatically captured in the modeling framework. Again, this is the mean of all the different months, and this is something I wanted to point out. So this is the observed range. This is the simulated range from the model, and this is what you would get if you simply interpolated the observations. So that's the difference. Okay, and the bottom is thought it would show up on top, because the bottom is the sample realization from the model. So you notice that the observations were only at some random points, but whereas with this model you can generate daily weather at any location throughout. And so these are at two different locations. And I think I'll stop there, and I'll continue this in my last talk. Thank you. Yep.
If you have rain gauge stations over a large landscape, you might have overlapping effects. You might also have spatial trends,
yes,
which you would model out before you have your simulation, which you can use for your grading.
Yes, in fact, that's a good question. And even in this one, if in this methane covariance here, the Z is a spatial Gaussian process. So in the methane covariance, you can add those kind of trend terms, and you can add in this part of the model, you can add those terms that are, if you see a trend, drift. So there is some of it already in the methane covariance itself, the SIL or the nugget effect that captures that offset and trend. But you can also add other things if you feel are important in this in here. So here we do find that there is a little bit of a trend component. A companion paper that I pointed out, I think it's here, and then so a companion paper that just got accepted in Annals of Applied Statistics, where we use this to model temperature. And temperature is, you want to model both max and min together, and you want to capture the joint covariance. And furthermore, Will did this for Colorado. Those of you that you know, it's highly non-stationary. So you have the Rocky Mountains in the middle and the desert plains in the east. So you have a you have a very complicated covariance structure. So we came up with some cool ways of doing it, and that is sort of a companion paper to that. But that's a good point. But what this allows you to do, in fact, in the reviews, one of the reviews pointed, well, this looks like kriging. Not quite, because kriging doesn't get you a lot of the things. Whereas here you can parsimoniously represent all these non-stationary. Intermittency, that's a big property of rainfall, because it doesn't rain all the time. So if you look at the binary series, 1 and 0, there's just ones occasionally, but most of the time it is zeros. And that poses real challenge to a lot of the traditional techniques. So that's why the GLM combined with the spatial process makes it a much more clever and elegant way. And this is something that people have been using to model extremes and a whole bunch of other things in space.
So let's thank Balaji again.
Okay.
So a couple of announcements. He's in that room as usual. There's a trip this afternoon to this fossil park for which 31 people have signed their names so far, and you know who you are. And Shankar is the point person for it, and he has the list. And the bus has 36 seats, so if anyone else wants to go, it's first come first served. Please contact Shankar. It'll leave at 2 o'clock downstairs. On Wednesday morning, as soon as everyone checks out, hopefully by 8:30 or so, the bus will leave to Chennai. And I have a list of people who have already asked their plans for tomorrow morning. If anybody wants to drop out or wants to drop in, let me know. But I expect the bus will be in our worst case, we can get some more later. That's it for now, I think.
So we come back here at 11.